All right, Unit 11, we're going to kind of combine all the sections into kind of like one note. So I'm going to give it to you right now, not long. Got other stuff that I'm going to kind of trickle in as we go, but for the Unit 11 notes, we're going to be putting them up right here. It's on transformations. What do you think of when you hear the word transformations? Transformers, the movie, right? It changes into something else. Okay, the car changes to a robot, or the robot changes to a car, or a truck, or whatever it is. Well, that's what we're going to be talking about here. Transformation is a change of something. So here's the actual definition that we get. To change the figure's location, orientation, size, to create a new figure. Basically, it's to map or to move an image. So you might slide a figure over, you might flip it over, you might rotate it around something, you might enlarge it, you might reduce it. Anything we do that to change it could be called a transformation. So in other words, we could say it's to map or to move an image. To map it onto another place or to actually move it somewhere else. That's a transformation. The pre-image is the image that's the original one, the original image before we transform it. It's basically the image that we start with. That's what we call the transformation, the pre-image. Image before we do any transformation. The original. The image we call the figure after the transformation. I'm not sure why they didn't do image and then post-image, but they did it the other way around. They did pre-image and then image. Image is what you get after you do the transformation. Isometry or isometry is when the figures stay the same size. So that eliminates a reduction or an enlargement. You don't reduce something or enlarge something when you have an isometry. Isometries are the exact same size. It preserves distance, is what it really is talking about in the book. It preserves the distance between points, so they stay the same after you transform them. That's what an isometry is. We have three kinds of isometries. Three kinds. There's three kinds of transformations that don't change the size. There's a couple that do change the size. An enlargement makes it bigger and a reduction makes it smaller. Those are not isometries. We do have three of them that are isometries. The first one we call a reflection. A reflection stays the same size. When you look into a regular mirror, you see yourself the same size. Now, if you look in a mirror that enlarges things, of course, you're going to be bigger or smaller, whatever. But if you look at something, the regular mirror, then you're the same size. That's an isometry. It's called a reflection. It uses a line like the mirror. This dot right here would be called the pre-image. That's the image before we transform it. Now, I call this line right here, I call it the folding line also. You could call it a line of symmetry or a line of reflection. You could call it either one of those two. I just call it the line where we would fold it. Because when you fold that line, this pre-image, this dot point P right here, would fold over this line and it would become P prime, which we call the image. And if you notice, the P has a little tick mark there. It just means P prime. With an apostrophe. It means you're still taking the same point P, but you're moving it, so now it's called P prime. You're not changing the letter. You're not making it a new letter. It's not a new point. It's the same point that you're just mapping to the other side. So you're taking the P and putting it as P prime. So that would be your image. So you got a pre-image where you start with, you move it, and it becomes the image. So in this second one here, here's your pre-image. Draw a little right triangle. Put points A, B, and C. Point A, B, and C on your paper there. Now, which point is closest to the line of reflection? So what point do you think on the other side is going to be closest to the line of reflection? A is. Because when I fold it here, this A is going to land on A prime, and B is going to land on B prime, and C is going to land on C prime. So that's going to look like this. So just draw in a triangle that you would see as a reflection. This is what you're going to be doing on the worksheet tomorrow. You're going to be drawing these reflections where you're not just recopying this to the other side. You're showing what would happen if you flipped it over. That's a reflection. If you flip the image over, folding it on that line of symmetry or that line of reflection. Notice how A became A prime right here. A became A prime. B became B prime. C became C prime. Same letters, you're just putting a prime next to it because you take that image and you flip it over. Good move. Okay, lines of symmetry. Figures have lines of symmetry. This square right here has lines of symmetry. So here would be one of them right there. Now I don't know, things get distorted on your paper, so I know it looks like a rectangle. Pretend it's a square. So above it, write the word square so you know that we've got a square here. That it was supposed to be a square on your paper. Okay, so put that down that it's a square. Now a square would have that line of symmetry. Would it have any other lines of symmetry? Yeah, there'd be another one going straight down. That would also be a line of symmetry right there. You could fold this right on top and it would land perfectly on top of it. Would a square have any other lines of symmetry? Both diagonals would be lines of symmetry. In a square, that would work. This one would, and this one would. So this one actually has 4 lines of symmetry. It just has to be where you fold one side on top of the other and they land perfectly on top of each other. You wouldn't even be able to see the bottom one because it'd be landing on it perfectly. So that would be, this one has 4 lines of symmetry right here. Now what about the star? I know on your paper it's kind of stretched, right? So on the paper, your paper itself, you're only going to end up with this one right here if I can find it. You're only going to have that one on that star that you have on your paper. Now what about if it was a perfect 5-pointed star? You would have 5 points because you'd be able to draw a line through here. You'd be able to draw a line through here. Actually, you would have one from each point there, right? You would have 5 lines of symmetry if it was a perfect 5-pointed star. The one on your paper is not, so it's just going to have 1. This one up here is pretty good, so I could probably draw in all 5. Right down here, this arrow has just 1 line of symmetry. You could fold this top part on top of this bottom part. Now that's a horizontal line of symmetry. This one is a vertical line of symmetry here. Think about the letters in the alphabet. Can you think of a letter that has a vertical line of symmetry? A does. If you look at the letter A, if you drew a perfect A, and you drew a line of symmetry straight down like this, that would land right on top of the other side. That would have a vertical line of symmetry. Can you think of a letter that has a horizontal line of symmetry? C. Okay, so if you have C and I think O you said too, C going across would have a vertical or horizontal line of symmetry. This would land on top of that. So you can kind of think of that in the practice problems that you're going to be working on tonight that are also on the website. They're on the 2nd page of the notes, or 3rd page of the notes. You're going to be using some of your letters, finding out which ones have symmetry and stuff like that. Okay, moving on. This is how we can use a reflection. Because of the fact that it's isometry, means that the sides are all equal. Means that one altitude is going to equal the other altitude. That means that the 3x has to equal the 4s. So I already put that there for you. That means 8 has to equal the half y plus minus 10, and the 5 has to equal the 2z minus 1. So it should be easy to solve. You just divide by 3 on both sides, and you get 4/3. This one would be easy to solve. You're going to add 10 and then multiply by 2. And then you get your 36. So using the fact that it's an isometry, we know that the sizes have to be the same. So we could set up equations and we could solve them because it's an isometry. The last one is easy. Add 1 to both sides and then divide by 2. And you get your z equals 3. So you could solve them easily enough just by knowing that the sides have to be the same, or that it's an isometry. Now the second isometry, and I didn't cover anything up, so you have everything written right down on your paper. But the second one is called a rotation. And it's when a figure is rotated or turned around a fixed point. It's rotated or turned. Hopefully you finish the top, right? Okay, so this rotation right here, if you look at this point down here, this is your center of rotation. This triangle right here is getting rotated around this point. It's like us rotating around the sun, right? So this is going to be rotated around a fixed point. Well, what if the fixed point happened to be the center of your figure? Could we rotate that around a fixed point? Could I take this and rotate it around that point? Yeah, I could. It would still work. Okay, so yeah, you could rotate it around a fixed point in the center. But that's a rotation. Is when you're taking something and you're rotating it around a fixed point. Now we have something called a double reflection theorem. And that's right here. Double reflection theorem for rotation. Okay, here's what it is. It's the image created by two successive reflections over two intersecting lines is a rotation. So if you do two reflections in a row over two intersecting lines, you're actually going to be doing what we call a rotation instead of two reflections. I mean, you could call it two reflections or you could call it a rotation. The angle of rotation is twice the angle between the intersecting lines. Now I'm going to show you an example of it here in a second. I want to give you a chance to get that down. You don't need this second sentence right here if you don't want to. That's just telling you that there's an example right here. This is the information right here. This sentence is just telling you it's an example. I mean, you can write it down if you want to. But it's just telling you you've got an example right here. Here's what it looks like. Whoops. Here's what it looks like. That's two reflections in a row right there. That's what that is. Two reflections in a row. So what they did is they took, and they messed this picture up a little bit, so I need you to fix it before you write it down. This should have been B double prime. This should have been A double prime. The book made that mistake. But if you notice, they first took AB right here, and they flipped it over the y-axis. And you got A prime and B prime. You see that flip right there? You just took it here and you flipped it over. Then they took this and they flipped it down on the x-axis. So now you got the B double prime and you got the A double prime. Really what you could say is that this is your fixed point, your center, and you rotate this down to here. And you're rotating B down to here. How many degrees rotation did I just do? 180. How much is each angle here with these two intersecting lines? 90. That's what they're saying, that it's twice the angle between the lines. The angle of rotation is 180. The angle between the two lines was 90. So it was twice as much. What was that? Between the two axes, the y-axis and the x-axis is 90 degrees. And the whole rotation would be a 180 degree rotation. So it's twice as much. So that's what that looks like. So this should be B double prime, that should be A double prime. And this actually becomes a rotation. When you do two reflections in a row, you can actually call that a rotation. So that's called the double reflection theorem for rotations. How we doing? Okay? We got the picture down? Moving on. All right. The third one is called a translation. Remember, we had three isometries. Three of them that keep the size the same. One of them was a reflection. The second was a rotation. The third is called a translation. That's where you slide a figure. You slide it from one place to another. Does that mean that the figure moves at all as far as turning? No, it doesn't. It just slides. So you can see that this triangle just slid down to here. Didn't change its direction. It didn't turn at all this way or anything. It just came straight down. Okay. To figure out how you get from your pre-image to your image, you use a vector. Remember vectors? We talked about vectors already. Remember, what do we know about vectors? Remember the clip of the movie? It has direction and magnitude, right? He's fighting crime with direction and magnitude. That's what he said. So direction tells you which way to go, and the magnitude tells you how far to go. So that's what a vector is for us. Get this to work. There it is. A quantity with direction and magnitude, or size. It's basically telling you how do you get from the pre-image to the image. That's what a vector does. It tells you how you get from the pre-image down to the image. So that is a translation. Just sliding. You're just sliding it from one to the other. All right, so you're sliding a pre-image to an image, and the vector tells you where to slide it to. So this vector right here might say, okay, go over 5 and go down 3. And that would be your vector. It would get you to that point right there. That means each point from each corner would be over 5 and down 3. Over 5 and down 3 and over 5 and down 3 for each point. That's what that means. Let's look at an example of a translation where we're sliding a point. So first thing we have is we have a vector from P to Q. Okay, now this could be from P to P prime if I wanted to. I put P to Q because I just wanted to illustrate what a vector was. And then that's called the component form. What that does is tell you to go over 8 and up 4. The coordinate form tells you that you need to add 8 to the x number and you need to add 4 to the y number. That's what the coordinate form is telling you. Here's what a vector would look like. You go from point P to point P prime, which we'll call Q. You go over 8 and up 4 to get there. So you went over 8, you went up 4, you got to the point on your graph. So your vector is telling you, okay, go over 8, go up 4. Now, how do I find the magnitude of that vector? How do I find out how far I went to go from one to the other? Because I know that it's telling me that I need to go over 8 and I need to go up 4. Okay, so I know it's telling me to go over 8 and up 4, but how long is this? This is the actual vector. How long is that? What do I do to get that length? There's two ways I could do it. You remember what this is right here, right triangle? What can I do? A squared plus b squared equals c squared. That's one way to find that. That'll get you the magnitude. Or do you remember that big distance formula? Big square root, right? X minus x squared plus y minus y squared. That would also get you this distance. But you could actually choose either way to get the magnitude. Use your Pythagorean theorem or use your distance formula. Both ways get you that. Now there is also a double reflection theorem for translations as well. So down here in this little box, this time you've got two successive reflections. I would just write down this underlined part. You've got two successive reflections over two parallel lines. And we call that a translation. I would just write down the underlined part. Two successive reflections about two parallel lines. And then I would draw the picture to show what it looks like. So you can see line A and line B are parallel. These two lines are both parallel. You flip the first figure or over the first line, then you flip this one over the second line. That became a translation. You took this first D and you slid it over to this one right here, and it became D double prime. You took F and you slid it over here, and it became F double prime. And same thing with letter E. So this figure is the same direction as this one. You just slid this one over. So this first pre-image became this image way over here. If you flip it twice, it becomes a translation. Two flips with parallel lines. The other ones, we flipped it with two intersecting lines. That became a rotation. If you flip them over parallel lines, it becomes a translation. So that is double reflection theorem for translation. That one you have to have parallel lines to be able to flip them over two parallel lines. The other one was intersecting lines. Maybe you can see that a little better. All right, we got just two slides left. Let's take a look at a couple of examples. Determine if each transformation is a reflection or not. You think the first one is a reflection? So that would be a yes. Yes, comma, reflection. You took this one and you flipped it over. What is it also? It's also, you kind of slid it, but if you have a line in the middle, then you would call that a reflection. So because the center line, that's a line of symmetry, you folded it over that line, it'd be a reflection. What about 2? No. Not. Just not reflection, it would be fine. Okay, lines of symmetry. How many lines of symmetry would the first figure have? Just 2? 4? So you're definitely going to have one right here, right? Or in the middle. Should move that over to the middle. About that. Come on. Move it over. Won't move. There. Okay, so there's one line of symmetry. The second line of symmetry that you know for sure would be this one, right? So you'd have 2 there. What about the diagonal? No. Not in a rectangle. Because if I drew a diagonal in here, this corner up at the top is going to fold down to here. It's not going to fold way over here. So only 2 in this figure right here. Only 2. What about 4? 4 only has 1. That's correct. Where would it be? Horizontal or vertical? Yeah, it'd be a vertical one. It'd be straight down the center. Can't seem to draw a vertical line at the center very well. Go on. But yeah, it would be in the center. That would be your line of symmetry right there. All right, last 2. Pretty easy ones. Copy each figure onto your own paper. Use the translation vector to draw an image. So I'm just going to have you just draw the translation on your paper, telling us to draw it over here. So what I want to do is think about my 3 points. So I'm going to take this top point, slide it over. I take this point, slide it over. Take this point, slide it over. My new shape is going to be the same shape, but it's going to be slid over from one side to the other. Just sliding it. Number 2 looks like a rhombus. They want you to slide it downwards. So it's actually going to end up on the writing for the next one. We'll just slide it over so it's not on the writing. Let's do it over here. So we'll just say that we slid it over so that it's not on top of the writing. But it would be a nice symmetry. It'd be the same size. It looks like a rhombus or a square that's turned, like a diamond. So that would be 2. Just sliding it over. Number 3 says use the double reflection theorem to create a translation. So I'm going to take this point right here and put it right on this side. You see where that one went? From here right to here. I'm going to take this point and move it over to here. And this bottom point is going to be way over here. And I'm going to draw in my figure. That's a reflection. That's what you're going to do on tomorrow's worksheet. You're going to be doing a reflection. Now, if I want to reflect this one again, this one's going to go way over here. This one's going to be close. This one's going to be back farther. And it's going to look like this. Now, do you notice that this first figure now is a translation where we slid it over? You just took this first one and you slid it over to here. 4 is pretty easy. You're just going to draw a reflection, upside down triangle there, and then back to a right side triangle, and you've got your translation, just sliding this one down to there. So that's how that works. Your practice problems are on the website. On the last part of the notes page, they're on the Unit 11 page. So get those done tonight.